Alright, so today we're going to do our lecture on the Charpy impact. So that shouldn't take too long. And basically that'll be it for today. And then next week we're actually going to do the lab for the Charpy impact, which, I say it a lot, but this lab in person is probably the most exciting lab. And of course you can't do it, but we're going to do our fake lab next week, and then we'll do the data reduction too for it. Alright, let me share my screen. So lab 3, I graded your memos for that. So the grades are on Canvas, so you could check them out. I forget what the average is on offhand. Actually, I didn't calculate it, to be honest, but it looked like it was a pretty good average this time around, just like the last few memos. So keep it up, and again, make sure that you always look at the feedback that I give you. And yeah. And lab 4, or memo 4, that's due today. So for the column, make sure you turn that in by 11:59 p.m. Alright, so today, again, Charpy Impact test lecture. So we're going to go over the lecture, doing some notes. And then I'm also going to show you guys a video for this lab, which I think will be kind of cool. So this is what the setup looks like. I'm going to mute it for now. Let's see. There should be like a wide angle shot. Alright, maybe not. Yeah, there you go. So this is what it looks like. Theirs looks better than ours, of course, but basically, and this guy can also crank it up. So you have like a pendulum here, and we put it up at some height, and then we're gonna basically hit a piece of metal down here, but we're gonna talk about that in the lab. But that's the idea for this lab. So this is what the metal looks like. All of these metals, they're notched like this for this test. And then we hit them on exactly on this notch, and then we break it. And then we'll look at basically how it looks like and how much energy the material could absorb before it actually fractured. So that's the general idea, and we're going to talk about the specifics today. Oh yeah, also we're going to be using different temperatures for these metals. So, like right now, this might be at room temperature. Other times we might put it in an oven for a while, and then basically take it out and fracture it as soon as we can so the metal is still nice and hot. Alright, so let me share my my iPad screen. Or before we get started, are there any questions on the memos or the labs or anything? Give me a sec. Always takes a moment. What the heck? It said I needed to download a plugin to share my screen for my iPad, which I've done many times. Alright. So there we go. And alright, that looks okay. Alright, I hate how it takes my video off, or it's not the default video for when I'm speaking. Anyways, let's get started. So we're doing the Charpy impact test. And so you guys already saw some of the clips for what it kind of looks like. So keep that in mind, but we're going to watch that video also at the end so we get a better idea of what we're actually going to do for the experiment. Alright. Alright, so this Charpy impact test, again, where we basically have a piece of metal, just basically like a bar, and there's a notch on this bar, and we're going to place it down on some, basically, I don't know, I guess a bench, and we're going to load up a pendulum to some height, and so it's going to have a lot of potential energy, and then we're going to release the pendulum, it's going to strike the bar that we have on the bottom, and it's going to fracture it. And then from our Charpy impact tester, it's actually going to give us directly the amount of energy that the bar absorbed on fracture. And we're going to do this test for different metals and also at different temperatures. So that's the main idea for the lab. And basically, something that we want to take of note here is that in our past experiments, we've been increasing the load gradually to induce strain and or fracture. So think about our first experiment when we had those different metal bars. We would gradually increase the load or increase tension on our material, and then eventually we fractured it. So that was over the course of, depending on the material, maybe a few minutes, or if it was faster, maybe like a minute, but still took a pretty long time. And same thing for the other labs too. Lab 2 was the same really as lab 1, except we didn't fracture it. We kept it in the elastic range. Then lab 3, that was the beam. Again, kept that in the elastic range. What the heck? And then, and again, that was kind of gradual loading as well. Lab 4, the column. Depending on the column, it might have fractured pretty fast. If it was a long column, it would have failed from buckling pretty fast. But again, it was pretty gradual. And in this experiment, instead of having this gradual strain that's being introduced, it's going to be really, really fast because we're striking this material with basically a hammer. So that's a big difference. Alright, so that's the kind of general idea here. Okay, and then for this experiment, from this pendulum, because there's this sudden load that we have on the material, it's going to have a very high strain rate because, we're deforming this and then fracturing it in such a very, very short amount of time. So basically our material, depending on the material, it's going to be deformed, almost instantaneously versus these other labs that we've been doing so far. Okay, so we already kind of said that above, but I'll say it again. So very high strain rates. Alright, so our material, it's going to absorb some energy once we hit it with our pendulum. And the amount of energy that it absorbs is the impact toughness. So you might have gone over that a bit in your 331 class, solid mechanics. But if you haven't, then I guess this might be a little new. But basically, yeah, for however much energy that our material absorbs, that's going to be the impact toughness. So different materials, they're going to have different toughnesses. So we'll kind of draw out a stress strain curve here and kind of show some of the different materials. And you're also going to see this once we actually do the lab. So first, let's define impact toughness. Make a little section. Okay, so let's draw our stress strain curve here, our old friend. Okay, so we have strain, and then we also have stress. Okay, so for some of our materials, such as like a ceramic or a piece of glass, they're not gonna have much toughness. So they can be strong, but they're strong, brittle materials. You might have gone over that in the beginning of your 331 class. At least I know I did. So they might be strong, but their toughness is very, very small. So basically how we would see this on the graph is it can handle, again, a lot of stress. So go like this. So it can handle a lot of stress, but there's not going to be much strain for when it actually fractures. So the strain at fracture might be around here. Okay, and that's going to be like, again, ceramics. So toughness, if you actually wanted to calculate how much toughness something has, that's the area that's under the curve. We're not going to be doing it for this lab, just because we actually can directly get the toughness that each material has, or the amount of energy that it absorbed, because we're getting that directly from our reading on the Charpy impact test setup. And we'll actually go over the direct equation for that later on, but really it's just the potential energy at the beginning minus the potential energy at the end. And you you can get the amount of energy that is absorbed, because you can have your potential energy up top in the beginning. That'll be high. It's going to hit your specimen, and because of that, it's going to lose some energy, and then you're going to finish at this lower height over at the end. So that's the, I guess, another kind of general idea. But if you wanted to calculate the toughness, you could do that directly from a stress strain curve here, or you just get the area under the curve. All right, so then we also have something that has large toughness, and that'll be like our metals. So you can think of something like aluminum. That's going to be really tough. So that might not be as strong as some of these ceramics, but it's going to be able to have a lot of strain. It can handle quite a lot of strain. We saw that like in the first lab when our aluminum bar, it was able to deform a lot more than some of the other metals, and you saw it neck quite a lot. Okay, maybe I should have drawn it to be a little weaker. That's okay. So you see here that this isn't quite as strong as our ceramics. We're only going up to some amount of our tensile stress. So it's not, the UTS isn't as high as the ceramics, but it's also able to deform quite a lot more. It can have a lot more strain before fracture. So because of that, the area under the curve is quite large, right? So it has a lot of toughness, or a very large amount of toughness. Okay, and then that's really what we're going to see in our lab, these kind of two different materials. But there's another kind of material that we can talk about too, which would be an unreinforced polymer. So I don't know, maybe you could think of something like some kind of plastics. So they're not going to be strong at all. I mean, you can even think of it like gum or something. That's an example that Dr. James uses sometimes. You think of it like gum. I mean, maybe not an unreinforced polymer, but basically it's going to be pretty dang weak, but it can have a lot of strain that it can undergo. So it's going to stretch a ton, right? Or like silly putty, anything like that. So it's not going to be very strong, but it can deform quite a lot. But because it's not strong at all, it's going to be, its toughness is going to be really small still. So this will look something like this. Okay, so our stress here, it can't handle very much stress, but it's going to be able to take quite a lot of tensile strain. And again, if we were going to get this area under the curve, we could get our toughness for that. Alright, so for our lab, we're going to be using aluminum, I think 6061T6, like we use quite a lot. And we'll be using, I think it's still 1018 and 1045 steel. I might be wrong on one of them, but it's two different steels again. So kind of the same materials that we use pretty often for our experiments. And what we'll see in the lab is that some materials, they can actually act different under different temperatures. That's another pretty important topic for this lab. So some materials, they might remain ductile for different ranges in temperature, and other materials, they're going to behave differently. So they might be ductile at some temperature, and they might be brittle at a different temperature. Alright, so before we talk about that, let's talk about our basic definitions of something that is brittle and something that is ductile. So, okay, I will first do that, okay? Just basic material property of being brittle or ductile. Okay, so if you have a brittle material, that's going to be a material that's going to fracture with very little to no plastic deformation. Okay, so that's going to be able to absorb a very small amount of energy on impact. So that would be something like our ceramics up here. Okay, so our strain, very small, and it's going to fracture with very little or no plastic deformation. So it'll be a clean cut, basically. Alright, so if you break glass, it's, you drop your phone or something, it's gonna shatter the screen, the glass screen, and it's gonna be very clean cuts for where it broke. It's not gonna be like the glass isn't gonna stretch out first or anything like that. Okay, then we have ductile material, so they're gonna have at least a noticeable amount of plastic deformation before fracture. So I guess we could think about gum again. So if you have a piece of gum and you pull it out, it's going to stretch quite a lot, and then it's eventually going to fracture. Okay, and then because there's noticeable plastic deformation, it's going to be able to take or absorb a higher amount of energy on impact. And then the fracture surface that we're going to have, instead of being a clean cut this time, it can be kind of jagged. So if you're going to look at your piece of gum, it's not going to be this clean cut down the middle. It's probably going to tear, right? Another thing, I don't know, like an eraser, that's going to kind of be jagged. If you were going to take your big eraser and break it, it would be this jagged surface. It wouldn't be a clean cut. Okay, so we'll say jagged, and this is in general. It's going to be a kind of jagged or rough surface. Okay, so any questions at this point?
No, I think we're good.
Okay. All right, so fracture modes now. So this is going to be different than when we just talked about a brittle material and a ductile material. Our materials, they can have different fracture modes. So I might have a ductile material, but when it fractures, it can be a ductile fracture mode, or it can be a brittle fracture mode. So this depends on the material, but it can basically fracture or behave like a different material depending usually on the temperature. Say ductile or brittle materials. So they can fracture in a brittle or a ductile fracture kind of mode depending on some external factors. All right, so the big one is going to be temperature. All right, so we're going to have an example. So steel is a good example. I don't know if this is like one of the, like a really repeated example that you often hear in engineering. Like there's that one bridge, which of course I forget right now, but if you're like, I know as civil engineering students like hate talking about this bridge that failed, and professors always talk about it, but Tacoma Bridge. Okay, so yeah. But anyway, so if we take this example of steel, it's going to be ductile when it's under high heat, but if it's cold, if it's under in a cold kind of temperature, it can act as a brittle material. So an example, I don't know if you can think about the Titanic, but the one that's often talked about is the Liberty ship. So let me stop sharing this screen. Let me share my other one. Okay. Alright, so it's this ship. I think it was like in World War II or something. So we have a steel ship here. So it's again ductile under a high heat. But if it's under a cold temperature, then it starts to behave as a brittle material. So the water is cold. This is a steel ship. And because it was in cold water, it started to behave as a brittle material. And I got a nice little crack in the ship. I'm laughing at me, it's not funny, but if anyone was affected, but yeah. So it affected, or it was under this kind of brittle material, or brittle behavior, I should say. And it failed from this crack in the center here. Oh, you can actually even see something a little more related to what we're talking about. So there's this high strain rate for this crack that kind of propagated throughout. And this crack, it acted as a stress concentration as well. And then it failed. Alright, so that's what we're going to keep in mind. And this is something that you need to keep in mind, if you're designing something in the future for how is this material going to behave at different temperatures. So you want to keep your operating temperature in mind. For this ship, it's gonna be in warm water, maybe sometimes, but it'll also be in cold water. So that'll affect how this material is going to act. So in hot water, it's going to be ductile, but in cold water, it can start to act as a brittle material. Okay, let's go back to my notes. Alright, so another big part of this lab is this ductile to brittle transition temperature. So it can also be, you can think of it like a brittle to ductile transition, but the term that is often used is called ductile to brittle transition temperature, and DBTT for short. So basically, let's think about if we're at some high temperature. At some point, once we decrease the temperature, what you might see for some materials is that it's going to start to behave as a brittle material. So there's going to be some temperature or some transition temperature where our material goes from acting as a ductile material to a brittle material. And basically, once you're designing something, you want to make sure that your operation temperature is going to be above that transition temperature so you don't have that possibility of failure. We're going to write all of this down later too, but that's the idea kind of at a glance. Okay, so let's write out the definition again. So there's going to be some transition temperature when a material is going to go from ductile to brittle. Again, you could also think about it from brittle to ductile. It just depends on if you're going from a high temperature to low temperature or low to high. Okay, so let's actually draw this out. So we're going to have temperature on the x-axis. I swear my writing has gotten worse over the last few years, not better. If you can't read my writing sometimes, then let me know. Okay, and then on the y-axis, we're going to have the energy that's absorbed, specifically on impact. Okay, so what I'm going to draw now is a little snake, basically. Alright, so there's our nice little our little snake. And what we have here on the left-hand side is a brittle material. Can't talk right now. So we have a brittle material, and then on the right, we have a ductile material. Let me actually change how this kind of looks. I'll put ductile up here, and I'll put brittle down here. Okay. Alright, so I say brittle on the left because you can see on our curve here that, let's say like there, that the energy that's absorbed on impact is quite low. And then on the right hand side for our ductile material, the energy absorbed on impact is quite high. So there's some point in between here where we transition from acting as a ductile material to a brittle material. And that's going to be that transition temperature that we talked about. Alright, let's go fancy here. I'm going to do a dashed line. Although their dashed line in this app is way too close still. Whatever, that's the transition temperature that we have. So I just kind of eyeballed it here. But this is the temperature when we transition from a ductile material to a brittle material. So again, basically, if you're designing something, you'd want to make sure that your operating temperature is going to be higher than this. Because if it's higher, then you're going to be, whatever material that you have is going to act as a ductile material instead of brittle. Because if we were operating below this transition temperature, we would be in that range right there. We'd be brittle, and our chances of material failure, they would increase. You know, we don't want to have a disaster like the Liberty ship, right? Okay, so I think usually this actually isn't, usually there's not an equation that is used for this because in reality, it's not like you just go from being ductile to brittle right away. That doesn't happen. It's going to be this kind of gradual change. So up top here, yes, we're going to be ductile and that's going to be readily apparent. And at the bottom here, we're going to be brittle. That's going to be readily apparent. But in between, in this range, in this curve that I just drew, it's actually pretty drastic. But some other materials, you might not have quite as steep of a slope. So you might have a slope that's like this or something in blue. So that transition temperature is going to be not quite as noticeable. And in that range in between, you're going to have kind of a mix of your material being both a little brittle and a little ductile. So to use an equation for this transition temperature, you can do it, but it's not going to be as useful because you're going to have, again, you're going to have this kind of mix of being both brittle and ductile depending on the material that you have. Let me draw another curve again. Alright, so in green, our transition temperature, might be somewhere like around there. So it's going to depend on the material that you have, of course. So once we actually do our lab, I'm thinking we probably will use an equation just for convenience, but just keep in mind that, even though we're going to use this equation to tell us, yeah, this is when the transition temperature is, for some materials, that's not going to be this drastic change. When 1 degree, it's ductile, and another degree difference, it's brittle. Okay, so let's we can define this too a little differently for our ductile to brittle transition temperature. So this will be the temperature that we have. Again, we're solving for temperature. When the impact energy is halfway in between the impact energy for the highest temperature that we have and the impact energy for the lowest temperature. All right, so if we're looking at our graph, I'll zoom out in a second. If we're looking at our graph, we could find this ductile to brittle transition temperature by looking at the impact energy for the highest temperature. So that would be right there. And then, so we're getting this impact energy over here. And then we're going to look at our lowest temperature down here. And then we're going to get that impact energy right there. Just take the average basically, right? We're going to add them and then divide by 2. And then we'll get our, let's just say for convenience that corresponded to this value here. So we calculated this value and this thicker purple line. And then we would go down and get whatever that temperature is. And that would be our transition temperature. All right, so we can do that again in our lab, mostly for convenience because, again, at least from what I've seen, when I've kind of done more research on this stuff, is that usually it's almost like a more qualitative definition for this transition temperature because, again, in between, you're going to have a combination of your fracture behaving both in a bit of a brittle fashion and a bit of a ductile fashion. And I'll show you guys some pictures also in a bit for what that fracture surface is going to look like. Okay, so let's add on a few notes here too. Okay, so again, not all of our materials are going to have this very steep slope that we see in red on our graph. We might have a more gradual slope like we see in green on the graph. So within this range, when we're starting to transfer from this ductile material up here to a brittle material down here, within our range here, when we're kind of shifting, we're going to have a fracture, or I guess a mode of failure that's a little bit ductile and a little bit brittle. So how that fracture surface is going to appear is also going to be different. So if we have a brittle material, once we look at that fracture surface, it's going to be clean cut, just like we talked about with glass before. And if it's ductile, that's going to be really jagged. So if we're in between, we're going to have kind of a mix of both. Okay, so and then ideally we want our transition temperature to be quite low. You could say that's also gonna, I guess, depend on the application too, but in general we want this transition temperature to be low because that's going to indicate that our material is only going to fail at low temperatures, at very low temperatures. Alright, so to do this, you can actually change basically the composition of your metal to try to adjust how that transition temperature is. So for, admittedly, I don't know very much about this stuff, but if you have like some alloy for your metal, you can change the composition a bit, and that will then change where this transition temperature is going to occur. Okay, so our graph that we drew here, or these two curves, these would be for low strength alloys, technically, but you'll see that it's got, depending on the material, we're going to have different behaviors for our graph. So let's first say, let me actually change both of these to the same color. I'll make this red too. So in red, these are going to be low strength alloys. Okay, but we can also have different metals or materials, I guess I should say in general. So we could have another material, I think it's actually like copper. My current graph I'm looking at doesn't say it, but I'm pretty sure one of the metals that we can have is copper. And copper is going to behave differently than these two metals that I drew in the graph. So let's use the ugly color of brown. Can copper be up top there? So let's say copper. And you can see that that's not changing very much for the impact energy that we have, or the amount of energy that is absorbed for copper on failure, right? When we're really hot, the impact energy is very similar to the impact energy when we're also really cold. What I drew here, it actually might even be a little more drastic than you would see in real life. So I should have gone through the lab again, the actual data reduction, just to make sure what materials that we actually have. Because it would be nice if we had a material like copper, so you could see that in the experiment. But honestly, I forget. But anyways, the point of this is that depending on the material that we have, the shape that we have for this ductile to brittle transition is going to be different. So in red, we have our low strength alloys that'll be like aluminum. Then up top, we have copper. That's going to have a different behavior. And even more specifically, this is going to be FCC metals, which I'm not going to pretend I know a lot about this stuff, but that's face-centered cubic. So that deals with how, like, the actual composition of the material. Honestly, probably some of you know more about this than I do, because I think we have a class at CSUF on this stuff. But I don't know too much about it, to be honest. And then in red, these would be BCC metals, which are body-centered cubic metals. So you can kind of think of them that way for how they're grouped as well for their behavior on this graph. Okay, so that's it for the theory, but I'm going to show you guys a few pictures now of the fracture surfaces that we're going to get, and then we'll also watch a video. It's a short video, but you'll see what the experiment kind of looks like. But before we do that, any questions? All right. Okay, so if you were going to actually do this lab, this would be one of the steps that you have to do, which would be taking pictures of the fracture surface after you broke something. So remember, we're doing this experiment at different temperatures for different metals. So these first two pictures, this is the fracture for, and actually, I don't know if this is actually correct. This picture here. I didn't supply these pictures. I got them from a different lab, actually. Anyways, this is the fracture surface for 1018 steel after being exposed to dry ice. So it's going to behave as a brittle material. So you see on the left here, it's a really clean cut. Here at this side view, it looks kind of jagged. I'm not sure if this is the right picture. Now that I look at it, it said it was in the document, but I'm not too sure. It looks a little too jagged. Could be though. Might be kind of an illusion. Okay, but point is, if you have a brittle failure, you're going to have these very clean cuts here that you see here. And then below we have again 1018 steel, and this is after it was exposed in an oven. So it was in an oven for quite a while, and we basically take it out of the oven and we try to run our experiment as fast as we can so the material is still nice and hot. So here you can see that this fracture surface, it's really, really jagged and unsmooth compared to this clean cut up here. And even more so, you can see that it didn't even fully fracture in the end. So, like it didn't, cut in half. So this absorbed quite a lot of energy, and I don't know what it was offhand, but it absorbed quite a lot more energy than the material. It's the same material, but it absorbed more energy than up here when it was exposed to dry ice. Alright, so that's kind of the, trend that you will see for some of these metals depending on the composition. This would be a body-centered cubic kind of material. But if we had something like copper, its performance, I guess if you want to think of it that way, would stay relatively the same if it was hot or if it was cold. Alright, so that's fracture surfaces. Now let's take a look at our video. So it's 5 minutes long. I guess, we'll actually go over this next time because this is more for the experiment, right? But I'll show you a few things now, just kind of skipping around. But then we'll actually watch it next class. And it's online too if you actually want to watch the full video. It's on our page for today. So remember that this is what our setup is going to look like. For us in the lab, we actually have to pull up the pendulum ourselves, and it's like 60 pounds or something. So we set it up to our initial height here. So we have our potential energy, we have our mass of the pendulum, we have gravity, and then we have our height. So we can calculate that potential energy. This is going to go down and strike our material, which has this V-shaped notch. That's for the Charpy impact. So we have this kind of localized stress concentration. So depending on the material, once we fracture it, you'll see it will either have a clean fracture there, or it's going to kind of bend outwards like we saw here. So that's just to make sure that we fracture at that surface or at that plane every single time. Okay, so it's going to strike down, it's going to hit our material, and then it's going to fracture. And this is going to tell us how much energy that our material absorbed on impact. So basically this dial, it'll go basically anywhere here depending on the material. And for us, for our lab, it's in units of foot-pounds. I believe that's correct. I'll make sure next week, but I'm pretty sure it's foot-pounds. And we'll get that directly from, you will have a spreadsheet, but in the experiment, we would look at this kind of dial and we could tell. And it's doing that from the basic theory of when we start at some high potential energy, we strike a material that's going to absorb some energy. So our pendulum is gonna finish at a lower height. So we take mgh in the beginning, subtract that by mgh at the end. The only difference is going to be the difference in the height. That's going to change the energy, and that'll basically give us the amount of energy that was absorbed for the material. Alright, see if we got any other cool things here. Here he's lining it up. And that's a better image of what the materials kind of look like before we test them. So there he's lining it up because this is actually a good note for your memos. If this is more aligned on, let's say, this right-hand side than the left-hand side, it's not going to strike perfectly on that notch we saw. So we want it to strike right there, but if we're misaligned, it might strike right here, and that's going to change how this is going to fracture. Alright, so we got anything more? There, he's reading how much energy it absorbed. Here they're just talking about what we actually just talked about. Okay, here. Now, so here it fractured, kind of a little side view. Here he's showing the top view, so this looks a bit ductile. It looks like a combination to me. So it's not really, really jagged, but it's also not completely smooth. It was actually more brittle, because we saw here. I forget the units for this guy, but here we're right around 13. And then if we go to the next material, I know that absorbed quite a lot. Okay, so he sets it up. This is over here now. I think it was 180. So 180 something. I forget. And then take a look at this. So this also didn't even break completely. So it was really, really ductile. It absorbed quite a lot of energy. And compare that, so that's right here, compare that to the first material that fractured. That fracture surface is a lot different. Alright, and then you also see what we kind of talked about at the end of the lecture too. Alright, so any questions before we sign off for today? Alright, well that's all I have for you guys today. So next week we're going to go over the actual experiment and then the data reduction as well. Some of it I want you guys to start doing a little bit more on your own. And yeah, don't forget that memo 4 for the column, that's due tonight by 11:59 p.m. And if you came late today, your memos for lab 3, they were posted yesterday. The grades. Alright, so that's all I got for you today. So if you don't have any questions, I'll see you guys next Monday. Alright, so have a good week.
Have a good one, Professor. Thank you.
Thanks, you too. Yep, thanks guys.
Professor,
Can
can I talk to you a little bit right now?
Yeah.